Welcome to a podcast on what is the standard deviation. In this particular podcast, we're going to talk about the standard deviation's definition and then talk about what we use it for. So notice in the previous work that we did, we worked with the interquartile range, which was a measurement of spread based upon the median. Now what we do want is a measurement of spread based upon the mean. Okay? So to do this, what we're going to do is average the distances from the mean of our data. In other words, we're going to find all the deviations from the mean, which will be the distances. That's their positive and negative numbers, so that's why they're deviations, but they're basically the distance. And we'll average that deviation from the mean. Well, in actuality, we don't do that. What we do is we sum the square of the deviations and divide by n minus 1 and then take the square root. But that's for another day. We'll go through the formula, explain why it is what it is, but it's one of those things you kind of have to take on faith at this point. So let me explain what this formula says. Here's each of the data points that exist in our data set. What we're going to do is subtract from every one of those data points the sample mean. Once we've done that and we found the distance between x and x bar, we'll square that. And by doing so, we'll make each of those numbers positive. Add those all up. Remember, that's what this guy right here does. This is the summation symbol, which means add them up. We'll sum the square of those deviations, and then we'll divide it by n minus 1. More about the n minus 1 as we move through the semester. Just trust us for the moment. Now, that average needs to have the square root taken of it because we squared it. So it's still the best way to think about what the standard deviation is. It's the average distance all the data points fell from the mean. So if you take all those deviations or all those distances away from the mean, and we add them all up, square them and add them all up, and then divide by n minus 1, take the square root, we've got that average distance from the mean. All right, now notice, and this is a very important point here, that in this calculation we were using x bar and little n. And so this number we just calculated came from a sample. So it is the sample standard deviation and is represented by a lowercase s. Now the calculator uses a sub x, the textbook will just use a lower s. It doesn't matter, they're interchangeable. If I had chosen to just call this s here, let me go ahead and change my pen back to block here. Let's go with a little bit bigger. In other words, if I had just said s, that would have been equal, okay? All right. Well, if there is a sample standard deviation, then there must be a corresponding population parameter that it must trying to estimate. The population parameter, it changes slightly in the calculation formula. First of all, first thing you need to notice here is that what? Well, it's each of the data points subtract the population mean mu, and that it's divided by capital N, which is the size of the population, and not divided by n minus 1. Now, if we calculate this population parameter, then we're going to use a Greek letter to represent it, and the Greek letter here is a lowercase sigma. So the way you would say that, the way that's read, is S-I-G-M-A, okay? That's sigma right there. And you may be going, wait, Mike, didn't we just say that this thing right here, this summation symbol, was also sigma? It is, but that's a capital Greek S. This is a lowercase Greek s, all right? Now, fortunately for us, our T83, 84 calculators calculate both the population and sample standard deviations. So let's go ahead and get the calculator up here, and let's see how it does that, okay? So clear out our box plots from our previous example, and what we're going to do is going to go into Stat, we're going to go to Calc, we're going to go to 1var stat, and we're going to go ahead and get the standard deviation of the age data. Hit and enter, and what we notice is that the calculator reports for us both the sample and the population standard deviation. It's up to us to interpret which of these two numbers is the appropriate one to use, okay? If we had a census, if we had every possible data point, then the population standard deviation, sigma sub x, would be the one we'd use. If we had a sample, we'd use s sub x. So in the case of our age data, since that was a sample with size n equal to 40, we'd use the sample standard deviation of 10.527 years. Now, one of the things about both the mean and the standard deviation is they carry the units with them that the base data has. In other words, if the data was in years, the mean and the standard deviation will be in years. All right, let's go back to our slides here. And one more time, what is the interpretation of the standard deviation? It is roughly the average distance of the observations from the mean. The more spread out the data are from the mean, the larger the standard deviation will be. Now, since the standard deviation is a distance, it is always a positive number, and again, it carries the same units as the mean, which are the same as whatever our data carried, okay? All right, here's a little example to explain exactly what we're talking about here. These are a set of data where the sample means in every one of these, oops, the bar fell off there somehow, let me go fix that real quick, where the sample means x bar for all of these sets of data is equal to 4, okay? So x bar is 4 for the first one, the second one, the third one, and the fourth one. But notice at first, every one of the data points with a frequency of 7, that all of the data points were equal to 4. So if every data point was equal to 4, well then by Jove, the mean would be equal to 4 and the standard deviation would be 0 because the average distance away from the mean is 0. Now if we take 3 of those data points and stack them up over 4, put 2 of them on 3 and 2 of them on 5, then we'll get a standard deviation of 0.8, okay? If we stack it up so that most of the data are on 3 and 5, then the average distance away from the mean is going to be about 1. Notice now that if I slide it out to 7 and 1 respectively, that this average distance away from the mean is about 3. So the thing to notice is that the standard deviation will increase as there's more spread in the data, okay? All right, so take a guess here real quick and see if you can decide which of these two distributions, which histogram, has a larger standard deviation. Hopefully you figured out that it was not this one. Nope, not that one. It's what? Yep, it's this one. Okay, now why is that? Well, notice that they have both approximately the same mean. It's somewhere around 2.5, but the data is more spread out in this distribution to the left and to the right than it was in this one. One thing to notice is the difference in the scale and the frequencies of these two histograms. If you need to, pause it right now and take a look at those two histograms until you get the idea why this one has the larger standard deviation. So this one has the bigger standard deviation here, okay? All right, let's take one more example here. So let's use the age from our subjects in the class. Let's find the standard deviation for these data, and then we're going to complete the following sentence. Okay, so let's go back to our calculator for a minute. We see the sample standard deviation was 10.53. Let's just go out to 3 places. So our standard sample deviation was 10.53 years. Let's make sure if there were units with the data, you should have units with your answers, okay? So complete the following sentence. On average, the ages of the subjects were about 10.53 years from the mean. Let's see, what was the mean again? Let's go back and take a look at our calculator and see if we can figure out what the mean was. The mean was 26.5 from the mean of 26.5 years, okay? All right, now, how many of the subjects had ages within 1 standard deviation of the mean? Okay, well, let's check that out. I've got to do a little bit of arithmetic here. Within 1 standard deviation of the mean would be what? Well, let's take a look at that interval. So that's going to be 26.5 minus 10.53. That would be the lower end of it. And then the upper end is going to be 26.5 plus 10.53. So we've got somewhere between 16 and 30, round off to a whole number here, between 16 years of age and 37 years of age, okay? So back at the ranch here, we're asking how many of them fall between 16 and 37. Okay, one more time, make sure you see that. Notice that the lower number, that's down 1 standard deviation from the mean. The upper number is up 1 standard deviation from the mean. In other words, take the mean and subtract a standard deviation from it. Take the mean and add a standard deviation to it. Okay, so let's go back and take a look at our age data. We scroll on over to the age. Now we notice that our ages are sorted, okay? And we see that what? We have 1, 2, 3, so that all those lower numbers are going to be in there. So we can come up here to where we find somebody who is older than 37. Okay. Keep going here. Let's see, we got 29, hit the 30s finally. 36, 40. Okay, so it looks like what? There were 35 out of the 40 numbers were in that interval. Okay. So between 16 and 37, there are, one more time, make sure you got it here. Where did I get that number from again? So you notice the position number right here, 35, that's telling me how many numbers I counted up to. Notice my first number was 16, so all the numbers below this 36 down, all of those are between 16 and 37, okay? So between 16 and 37, there are 35 numbers, right? That's one way of saying it. That'll work, okay? Or ages, actually. Let's say ages. I think that's a better way of saying it. Okay, how many of the subjects had ages between 2 standard deviations of the mean? Well, let's take a look at that. So to do that calculation, let's go back out to the home screen. And notice that what we're looking for is 26.5 minus 2 times 10.35. Excuse me, 5.3. 5.3. There we go. Ooh, yeah, I think we've widened this interval up pretty much to include just about everybody, if you ask me. So let's go get the upper end now. By the way, to replay a command, you may notice that I just did that. You hit a second and an enter, and I don't have to retype the whole thing. And it looks like between 2 standard deviations, I got to go up to, let's go ahead and round up to 48, okay? Whoops, let me back to the calculator here. Well, so let's put it down first. So we're going to be between those two numbers are going to be between, let's see, better do a little rounding here. We'll go 6. Well, we'll go 5, but heck, we'll round correctly. Between 5 years of age and 48 years of age. So okay, all right, so go back to our data set, go to Stat, go to Edit, go to Age, and I'm going to go up this time because where was our number again? Let's remind ourselves real quick what we were looking for. All the values that fell between where and where? Between 5 and 49, right? Okay, so between 5 and 49, looks like, I'll get the right spot there. There are 38 of the 40 numbers fall between those two numbers. Okay, now, turns out that little exercise that we just did there turns out to be an important concept. We're going to come back to what we just did there many more times through the semester, that little trick that we just did about looking at the number of standard deviations above and below the mean and how many data points we expect to fall in there, okay? This is just an introduction to it at this point, and that's about all we got to say about it right now. Okay then, we'll see you back here for the next LDI.